Hello guys, hope you're all doing well. My name is Henry Roberts. I'm a rising sophomore in the engineering school majoring in aerospace engineering. I live in Montclair, New Jersey, about 15 miles outside of New York City, and I really can't wait to go back to campus in the fall. For my final project, I did Unit 6, Distributed Loads and Internal Forces, with respect to the Arc de Triomphe in Paris, France, and Units 7 and 8, Stress and Strain and Material Properties, with respect to the cables holding up the lights in my kitchen. Hope you guys enjoy my presentation and learn something new about cables or arches, and enjoy! So this is a picture of the Arc de Triomphe that my dad took last time he was in Paris on business. He always used to send me postcards, many of which had pictures of the Arc, and as a little kid I thought it was kind of fascinating, because here's this huge slab of stone supported by these two, I wouldn't call them small, but the legs that certainly do not look large enough to hold up that much weight. For my project, I chose to analyze this structure with regards to Unit 6, Distributed Loads and Internal Forces. I wanted to figure out how something so massive could be supported like this. I also wanted to learn more about arches, because as a kid I was a huge fan of Roman architecture, and I always wondered how huge structures like the Colosseum or the aqueducts could be supported with the technology they had at the time. This is a scale drawing of the Arc that I did. It's definitely more simple than the real thing. I'm not much of an artist, so I had to leave out the detailed sculptures and engravings. Each unit on the paper represents 2 square meters. The Arc is 45 meters wide, 50 meters tall, and 22 meters deep. While the drawing is to scale, there's no true way to articulate how small you feel standing next to it. My dad said he felt like an ant next to it. After all, it was built to symbolize the conquests of Napoleon. The Arc is made almost entirely of limestone with limited wood, iron, and steel supports. For the most part, the structure is just a huge self-supporting limestone block. As you can see, above the Arc there's a massive slab of limestone, almost 20 meters tall, that looks monstrously heavy. Real quick, we're going to go into how the arch actually works and what its components are. As you can see in the top diagram, points labeled B are called the voussoirs. They carry the forces down the arch into the footers. Point C are the footers. The arch rests on top of them and they capture the remaining downward force. A are the abutments. They balance out the horizontal components of the force created by going down the arch. They create what is called arch action, where tensile stresses are converted into compressive stresses. The keystone, which is maybe the most important part of the arch, supports the load and distributes its forces into the voussoirs. Looking at the bottom diagram, you can see the distributed load W resting atop the arch. This is whatever the arch is holding up. R is the radius or the rise of the arch, and L is the diameter or the span length. As forces are carried towards the ground, the arch will push them outwards. They are then counteracted by the inward force at A, and this is known as thrust, where forces push outwards as they get down on the arch. The question I decided to ask for my worked example was what the horizontal and vertical components of the force in the legs would be. There's approximately 20,601 cubic meters of limestone resting above the arch on the Arc de Triomphe. Using limestone's density, then converting to kilonewtons, we find that there is a total distributed load of 11,497.4 kilonewtons per meter resting on the arch. Using this knowledge, we can find the forces that need to be exerted by the legs to hold up the arch. Since the arch redirects forces outward along the curve, an outward horizontal force is created. The force in the legs need to balance out this force, as shown below. I found the vertical component of this force to be 258,691.5 kilonewtons, and the horizontal component to be 398,123.03 kilonewtons. The information above shows us that each leg exerts an extreme amount of force in order to counteract the horizontal and vertical components of the distributed load. The arch shape redirects loads out along its curve, allowing for heavier structures to be supported than other methods like columns. Where a column would only support weight by exerting a vertical force, an arch allows for the material in the legs to exert a horizontal force, alleviating tensile stress and holding the structure together using compression. Hello guys, welcome to my kitchen. As you can see, we have these 4 lights that light up about half the room, and they're held up by these 2 parallel cables. I decided to look at how much the tension in each cable would be, and then I got kind of curious about how many lights I could stuff onto this cable before the cable would break and the whole thing would come crashing down. To find the tension in each cable, I drew this beautiful free body diagram of the cable with each of the lights at a position on the cable. I didn't have any way to accurately measure the vertical of how far down each light drooped on the cable, so I had to kind of guesstimate, but other than that it should be pretty precise. First, I drew a free body diagram about point D and found the tension in cables BA and BC. From there, I found that both of the cables had around 8.51 pounds of tension in each. I then used that information and I plugged it into all of my other free body diagrams to find the other tensions. I found that overall the tension in the cable was around 8.51 pounds. After finding the tension in the cable, I wondered how many lights I could stuff onto this cable before it break. I got on the internet and found that the yield strength of steel was about 250 megapascals, and that the diameter of the cable I used was about 3/32 of an inch, or 0.093 inches. Using the formula yield strength equals tension over cross-sectional area, I found that the maximum tension in the cable was about 250.19 pounds. Assuming that I hung every light at the same point on the cable, I solved to find the weight max and found that it was about 13.25 pounds. I divided that by the weight of each individual light, being around 0.1825 pounds. I found that I could fit 72.6 lights on this thing before it snapped. To be completely honest with you, I think that the cable would probably get pulled out of the wall before the actual cable gave out. That's okay. That was a lot more lights than I was expecting. Thank you guys for coming to my presentation. I hope you were just fascinated by the forces that act on an arch and by the peculiar light fixture that I have in my kitchen. I hope you learned something. I hope you enjoyed. Thank you guys. Have a great day, alright?